After this last talk by Letícia, please go collect, if you have not done so yet, please go collect your money, okay? Okay, from you, okay, yeah. Okay, so it's my pleasure to have Professor Letícia Paiva here. Letícia did her PhD at Universidade Federal de Viçosa, right? And now she's a professor at the Federal University of São João del Rei, which is another nice university in Minas Gerais, a big and nice state in Brazil. Thank you, Letícia. The floor is yours.
So, is it working? Okay, thank you very much for the invitation, for the opportunity to talk about my work. Let's start. First, before to actually talk about the work I'm going to present, I'm going to show what we have been done with termites. So really quickly. First, we investigated the trajectories followed by a single termite. We did that by means of mean square displacement and these Kolmogorov-Q functions. And essentially, we observed that they have this super diffusive behavior. Then we include social interaction. So the density of termites in the arena is for us this measure of the density. And we could show that levee flights emerge as density increases. So this is the trajectory of a single termite, and we visually can see here. Here the power laws that become more clearly as we increase the density. And also we proposed 2 different models for these trajectories. Then we studied the social context, because in these previous works, we studied just workers from this. It's all the same species of termite, okay? But here we include soldiers, and we change the proportion between soldiers and workers. The levee flights are robust. The exponent changed, but just a little bit. The mean speed also is just modulated by this. And then this approach that we use the visibility algorithm to turn the series of step lengths followed by the termites into graphs. So it's a really nice algorithm. So we can, this is the visual approach for this algorithm, 2 cases. And we observe that then with the graph, you can analyze it through tools from complex networks. We see that the degree distribution probability is quite different. It's an exponential decay for a single termite and a power law decay when you have a lot of termites. And it seems that we have a maximum of complexity at intermediate densities. So this is what we did before. And now we are going to inspect the termites through the eyes of active matter. Just for short, active matter can be defined as active particles consume energy to move or to exert mechanical forces. These particles interact among them, and then they move synchronously and in a correlated way. In doing so, collective behavior and pattern formation spontaneously emerges. Here, I'm showing 3 examples from the literature of non-alive things that work in a kind of a similar way. But biological systems are the paradigmatic example for active matter. So here, we investigated groups of workers from these species, these corn-termis cumulans in circular arenas. We observed emergent phase in those groups. Milling, I'm going to talk more about it. Clustering, and this disordered behavior. So we are going to describe and parameterize them and their transitions. Our methods, for shortly, now I have a lab in my university, And we work with these termites because there are a lot of nests close to my lab in the gardens of the university. So we just leave the lab, go to the gardens of the university, take some termites, go to the lab, put them, for example, in this case, in a petri dish. We film them from above. Then we track the termites using a software developed by us. And here we, okay, this is an example. So we track all the termites in the arena, obtaining each one position. In this case, they are in this disordered behavior, so we cannot see an emergent pattern. We also define the angular position. So we have this angular position here, and this is the turning angle, as you can see, defined in this picture. Now I'm going to show a video when we have a transition from the clustering to milling. In the beginning of the video, until this point, we have most of the termites clustered together in an almost solid-like phase, doing just small movements. But eventually, a couple of them leave the cluster, goes through the arena, and comes back. Now they are becoming more disordered, and they are going to this movement, and now there's no this clustering phase. And if you wait just a few seconds, they will start to do this milling phase. Of course, it's faster than in the real. So they are kind of a flow, like a liquid phase. So we have this transition from one behavior to another. And we also observe this coexistence between these two behaviors. So these termites in the middle will stay in this clustering phase. Here, they are doing just these small movements to make contact with their neighbors. And another part of them doing this milling movement. Okay, our previous work emphasized the role of density in the emergence of each one of the behaviors we studied up to now. And so we, of course, want to understand what's the role of density in this emergence of milling. Then we did 20 samples for each density, in this case, this number of termites in arenas with the same size. And we observed that milling is more likely to occur at low densities. By the other hand, clustering is the opposite. We did not observe at low densities, and if in this case, when we have 70 termites, there is a 90% of chance to observe this clustering behavior. The trajectories, so I superpose the trajectories of all the termites, and they are quite interesting, but we cannot say nothing about the phase just looking at these pictures.
Can I ask something very quickly?
Sure.
Are you able to expose the termites to something in order to increase activity, increase persistence along some direction? I'm not sure. It's a biological system, so I'm just wondering whether you would have this tuning parameter.
Okay, we could do that in the experiments, but as I'm a physicist in doing this kind of experiment, I prefer to do not use any kind of pheromone and food, water. I just put the termites in the arenas with nothing and try to understand just their behavior by themselves, with anything outside. So after that, we, in a more controlled environment, because to deal with such things is really complicated, we can explore these things.
Okay, that's good. Thank you.
And if we take a look of just this temporal x-series position, now we have a signature of the phase. Here, in this part of the experiment, this is a frame. We do not have any emergent pattern, so it's a disordered behavior. And here we have, it seems that the amplitude of the oscillations, it's a little bit lower. And we have the milling phase in all this time. If you zoom in into this region, we see this kind of well-behaved oscillations, which is consistent if you try to imagine that the termites are doing this circular movement through the arena. This clustering, we also can see it. Here we have this disordered behavior, and now in all this period we have this clustering. So this is the track of just one of these termites, of course. Just small movements, then it goes for a walk through the arena, comes back, just small movements, around trip again, and it do it until the end of the experiment. As it's a standard thing to do in statistical physics, we study these displacement fluctuations. And in spite of these are two different phases in both cases. So here we have the transition from a disordered to milling, and in this case, a transition from disordered to clustering. So in both cases, we observe that these fluctuations decrease. So you have this transition from the disordered to organized state, in both cases described hopefully in the same way. We also studied these angle fluctuations. In these two cases, we have behavioral transitions, here from disordered to milling, from disordered to clustering. These gray curves corresponds to each one of the termites in the arena, and the black curve is the average of them. And in this case, when we have only disorder, we have a simple decay. Okay, so now we are going to take a look at this angular displacement. Each color corresponds to a single termite. So in this case, we had 14 termites in the arena. And we are going to divide this series in 5 time windows here. And we are going to characterize those series through local roughness that can be defined in this standard way. And we know that it can scale with this H exponent. That's another well-known exponent. It's called the Hurst exponent. And if it's lower, bigger than 1/2, it's a signature of a positive autocorrelation. Lower than 1/2, anticorrelated behavior or anti-persistent behavior. And if it's equal 1/2, we have a random uncorrelated behavior. So we are going to, just for simplicity, show just one of these curves in this first time window. We measure this local roughness. It's these red circles. And this dashed line is just a guide for our eyes with a slope of 1/2. I guess you will agree with us that in this case we have an exponent. It's not a fit, but we have an exponent about 1/2. And then we are going to do the same for the second time window. It is increased a little bit. Now, for this time window, now it increases again. And here, when we have this series here, this fourth time window, now the slope is really close to 1 when we have high persistent behavior. And finally, in the end, we have an exponent really close, even closer to 1. And we can observe that in this series, about 1/2 of the termites are going the clockwise direction, and the other 1/2 in the opposite direction. So they They do the movement in different directions. Okay, so it seems that this Hurst exponent is a good way to characterize the phase. We are going to obtain the mean Hurst exponent, consider all the termites. I show it just for one of them in each time window, and consider independent experiments, we get a range of mean Hurst exponents. Another way to characterize is through this mean velocity. In this specific case, we have a transition from clustering to milling. As we could expect, in this clustering behavior, the velocity is low because this is the average across all the termites in the arena. But most of termites are doing just small movements, so it's expected a low velocity. In this milling phase, as the termites are kind of know where they are supposed to go, they are faster, so we have a bigger velocity, and the disordered have an intermediate value. We did the same, so we are going to divide our series in 5-time windows, consider independent experiments, and we are going to get a range of pairs with mean velocity and mean Hurst exponent, which can be associated with each phase, as you can see here. So in this case, we have a lot of experiments. These arrow bars are because we have this average, considering all the termites in the arena. And here, for Hurst exponent about 1/2 and lower values of the velocity, all this case we observe clustering, milling really high values of the Hurst exponent and high velocities, and disordered with intermediate values. And a standard way to characterize animals.
Letícia, can I ask you a question?
Sure.
Can you come back a little bit? So the velocity, I see what it does, and we saw they were going faster, so it's kind of clear. Now, this Hurst exponent, what is can you come back to the definition? Because
Sure.
I can't see the physical interpretation. Oh, wait. So that's
Yes.
what, okay, it's in the angle.
Yes, yes.
Okay.
It's in this series.
Okay, so now
Okay.
I see.
So here we have this random behavior, and here persistent behavior.
Okay, I see. I thought
Okay.
it was on in the position. So okay, I see.
So this there is a lot of animals who which do this circular movement. Fish, sharks, ants. And a standard way to characterize is through the angular momentum. Here we have to consider this absolute value because termites can do this movement in both directions. As we could see, for milling you have a strong rotation, clustering a small rotation, and disorder in the intermediate values. Again, this curve is an average across all the termites in the arena. And our last measure, this mean turning angle standard deviation. Let me explain. First, I did not show, but this turning angle, it has a bell-like shape for all the cases, centered in 0, so we do not have a preferential direction instead of course, 0. So it's a persistent move in all the cases. But this standard deviation of this turning angle is a signature of these movements. Because when they are in this clustering, they are doing just this small movement, but they are trying to make contact with almost all the neighbors. So this angle changes a lot. By other hand, when they are in this milling, again, as they are kind of new where they are supposed to go, this angle does not change too much. So we have a lower value of this turning angle standard deviation. And again, disorder in the intermediate values. Here we have a heat map, consider 12 independent experiments, where we observe milling most of the time. And they are consistent, which we could expect. So strong rotation in all cases, and lower values of this turning angle standard deviation. For clustering, again, so in this case, the system stayed in this disordered behavior for a while, but then they clustered together with this higher value of this turning angle standard deviation and weak rotations. These are 4 independent experiments. For this disordered behavior, intermediate values of both. And we can also see these behavioral transitions. In this case, it's about a half of the time in this disordered behavior and the other half in the milling phase. Here, it's taking a while in this disordered behavior, and then this milling behavior emerged. Summarizing, we can classify these observed behaviors in such a way. Of course, these rectangles are just a guide for our eyes. We do not have precision to do these borders like that. And I had to change my presentation because this paper was accepted yesterday. And now, if you want, you can download it. It's, of course, it's the version we submitted, not the which one they published. But they will not care about that, I'm sure. And what we are doing right now. There's a master student in the lab, and his main goal is to understand the role of the borders, of the boundary conditions in this kind of behaviors. So we have such these big arenas. Here is not exactly milling, but it's a kind of. It's close to the borders, but not too close here. And in this case, it's 80 centimeters here. So it's a really large arena. He's studying considering small square and triangular arenas. We observed a squared milling. So, of course, these borders of the arena, they have an impact on this behavior. But also, we observed this circular kind behavior in an arena with the same size. He's studying the stability of the area of these patterns, and if it's related with how long it takes to eventually disappear. Up to now, we did not found any correlation, but we are working in this thing. We are struggling with a mathematical model because we already did a lot of versions, but no one of them we could observe milling and clustering. We could get some models when we observe this milling phase, with other rules, this clustering, but we could not get a model with which would be able to show both phases. We are working on it. And we still do not know what triggers these transitions. In some cases, in the first minutes, we just put the termites in the arena and they do this milling behavior. In other cases, they are in this random, disordered behavior or even cluster, and after 50 minutes, they start to do this milling phase. So we have no idea what triggers these transitions. I'm really proud because this is the first contribution from my lab. So this work, we could do it from the very beginning until the end in this lab in my university. So we did all the experiments there, all the analysis. All the softwares were developed by us, from the tracking to analysis. So it's a handmade process. I could not lose the opportunity to talk about parenting science. I'm a proud member of this movement. I'm not sure if you knew about, but it's a movement which at first wants to emphasize and to study, to investigate how the parenthood affects the career of mothers and fathers. And then we have proposed a lot of public policies. We did a lot of studies, a lot of analysis. And I will invite you to just parentingScienceAltogether.com. We are in all social media also. So please consider to follow us to know a little bit more about our movement. I have to thank the funding agencies, this really nice event. So here's the co-authors of the paper, Sidney, Otávio, Woggy, both are physics, and here's the termite guy, the students which help with the experiments, and Silvio Ferreira, who helped me when the funding agencies did not. So thank you very much. Comments, questions?
Thank you, Letícia. Very nice talk. Luis?
Thank you. Is this dynamic going back and forth, so it goes into the milling phase and then goes back to the clustering and back to the milling phase intermittently, or it always goes to the milling phase and it stays like that forever?
No, we track and analyze just for 1 hour. So we could observe in a few experiments the 3 phases, but I'm not sure if we waited too much time, if the system could eventually go back to the other phase. But one important point, what's explain why it's so difficult to observe, is that role of density. So milling is more likely to occur at low densities and clustering in higher density. So usually it's not really common to observe both behaviors. The transitions, the more common transitions are from disordered to milling. So in this case, as we can see, disordered to milling a lot of times, or in the clustering case.
Hi, Letícia. Thank you. When you do a new experiment, do you clean the arena?
Of course, of course. It's important because of the pheromones.
Yeah.
But in other projects, we are studying the effect of the pheromones left in the arena in the walk of other termites. But in this case, we wash everything, we clean everything to be sure. We do not put any food and water, and we try to take care to avoid any other aspects to make any noise, anything in your behavior.
Yeah. And about Danilo's question, how to control experimentally the persistence of these, the persistence length of these guys, right? So it's not immediate, right? I mean, how would you change how persistent they are in their directions experimentally?
Experimentally, could we eventually put something that attracts them in some region, or the opposite, to put something in the opposite side?
Yeah, but then this would be like a drift that the particle is doing towards some point. It would not be the free particle behavior changing, right?
Yeah, of course. We could
maybe you can
maybe some slope.
Yeah, maybe you can increase the temperature around so they will be less persistent, or you can make them drunk. So it will be
oh,
less
they drunk.
persistent
This termite guy I showed before, he had a paper but not the trajectory. He studied just the survival of the termites, putting in each one an insecticide. So it's really bad, but
like panic state.
yeah. The main properties remains the same, which is that these termites, they have optimal density where they live longer. So independent of the resource. So possibly we have these optimal social interactions for them, then they live longer in this. But to do anything to make they want to prefer to go for some place or not, the first thing that comes to my mind is to use pheromones. So we would be sure they are going to that place. But it's too complicated for me, so I will avoid to do this kind of thing.
And just very quickly, the models you are using, that you are trying now, are they Levy-Walker or ABP, active Brownian particle models?
Neither. We are trying to put the less number of ingredients and see what emerges. So we tried correlated behavior with this for each one of the termites, and we consider the pheromone released by them as a kind of a guide to do that. So we could reproduce that milling, but not the clustering. And importantly, I did not say they are blind. So it's a problem.
Yeah, so in the pictures of the large arena that you showed, it seemed like the milling was hugging the boundary quite sharply. Do you see that behavior just generally, that the milling hugs the boundary of the arena?
Did you see that they are close to the borders of the arena?
Yeah,
Yeah.
I was assuming that those were the milling termites, but maybe not. I mean, I guess what I'm asking is, when they mill in large arenas, do they tend to mill basically around the perimeter or not?
Yes, it is what it seems.
Yeah.
I have to confess that I hope that they do, for example, here, a milling trajectory here, completely independent of the borders of the arena. In this case, the borders, we can say, oh, they are not touching the walls, but it's too close. So I'm not really convinced about this emergent behavior in this case. Here, we have a small different way here, but also it's in progress, because what I really would like to observe is they, for example, here in any place far from the walls, doing, let's say, a small milling here. I'm not sure if we are going to observe that, but this will be something that we could say, okay, this behavior happens in spite of the boundary conditions.
And I guess one other thing is, when you have sort of coexistence of milling and clustering, and you look sort of across trials, have you ever tracked individual termites across trials and said, oh, this one has more of a tendency to join clustering groups or milling groups, or are they all kind of equally likely to mill or cluster when both are occurring?
We did not do anything like that. We can see which one starts to do the movement. For example, inspect that X-series position, so we can see that. But what we can observe, for example, in this clustering, we have a lot of termites clustered together. A couple of them leave the cluster, goes for a walk. Then they attach, and other couple leave the cluster and goes for, let's see what's happening in the neighborhood. But that's not the same. But this is something I'm telling just in visual inspection. We did not measure anything like that. In the milling case, we have, for example, there's some case that we have 14 termites in the same direction, and one of them for 1 hour in the opposite direction. And we do not know anything about a kind of a leader, someone who would guide. And so We do not know, but I guess it's not the case. Oh, sorry.
Okay. Thank you very much for the presentation.
Thank
I
you.
was really impressed and I loved it. I have some few questions, please. My first question is, how often do you change the samples? The samples you have. You said you go to your garden close to the school and you just pick new samples, if I heard them well. I think so.
With samples, did you mean different independent experiments?
Yes.
We did more than 200 experiments, independent experiments.
Okay. That's
No,
the question.
the single termites. The
Okay.
single termites, the same species, in all cases workers. We try to choose the same size because... No. Each individual is can be used only once. It's
Okay.
something that it's
Okay.
ecology. They don't know if they are used in one experiment. Unfortunately, they go to death, and we have
Wait,
newer
okay, they die.
termites.
After this, they die, right? That means you mean after the experiment, they are dead. Is that what you're saying, the termites?
These termites.
Yes.
I did an experiment with some termites. So after that, I will wash everything, change the paper, and the termites will be put in a place, and we are
Okay.
going just to wait them
They
to
die.
die.
Okay. Thank
They
you.
made the contribution to science. We thank you them, but
Okay, you talk about the size, but also I want to know is the age of the samples. I know they have a life cycle. They die after a particular period of time. I mean, the termites. So the samples you take, at which stage are they concretely? I mean, the termites. At which stage in their growth are they? I know you said they are workers.
did you say about the age of the termites?
Yes.
Yes, then we try to select termites with the same age, selected them by size, because the younger ones, they are a kind of brown. They are not too black. And the size of the termite is also indicates its age. So we try to choose similar termites, because for us they are, until proven the opposite, identical particles. So we try to choose them in that way.
The last question, please. Actually, you said that you are building a model. You are building a model, mathematical model. But I know that the Schomalator system built by O'Keefe, the XY model built by O'Keefe and all, actually has some of these dynamics, because what you just showed, clustering and the turning around, it's basically similar to what we call the boiling state from the O'Keefe's model. And also I observed some other recurrences, like the directions. The graph showed the directions. I don't know if you did there from one of the slides you showed theta with time.
Yeah.
And there we had various directions which the termites were taking. Actually, it resembles the phase, the internal dynamics over time that the O'Keefe model produces. So actually...
those just milling we can reproduce.
Okay.
But I would like a model which could reproduce both milling and clustering. Hopefully with a parameter which we could turn and, in this case, because this would be something that will give us a guess about how are the underlying mechanisms and how the system works. So I'm looking for a model which can contribute in this understanding. And up to now, we could not get. But just for milling, we get it.
Hi, very nice talk.
Thank you.
I have a question regarding the experiment itself. Do you have any control about temperature or humidity?
I forgot to say. We are studying that. In these experiments, I just took notes. So I have this. As we take the termites from a few meters from the lab, so we do not control temperature in the lab. neither humidity, because we say, oh, if it's happy there, it will be happy here also. But we tried to do a kind of a way to control the temperature, because we still are not sure if the temperature isn't really important. Probably it's not, but not too important. But we, up to now, we see that above some temperature they die, and below some temperature they start to move less, and even they could make really frozen. But it's reversible. If we turn on the temperature, they go back and can move again. But we still could not do this experimental thing, which we can control this temperature for studying in the really nice way with taking care of other things. But it's an open thing that we are still working it. Thank you.
Here's,
What?
yes.
What does one termite do?
If you take only one termite, what they do? I think this is their first work.
Yes. There is no...
Does one termite do circles?
Oh, probably yes. Circles, yes. What we observed, that was, as Carolina remembered, the first experiment, the first slide, we characterized just the trajectory of them. Probably they do this milling, but because they are doing this movement and leaving this pheromone, and possibly they can follow his own track. So it happens, but it's not something quite interesting to see. And this clustering behavior, of course, it doesn't happen. It has those parallel waiting time decay. So it eventually stops and stay for a while, but it's not something like this clustering behavior. So there is no this emergent phase if you consider just one. But rounding close to the borders of the arena, yes.
Okay, more questions for Letícia? If not, let's thank Letícia again.
Thank
for
you
the nice
very
talk.
much. Thank you.
And again, for those of you who had not gotten your money yet, do that so now, please. Thank you. And you'll come back tomorrow at